Hey everybody, looking at friction today. Hopefully you read through the PowerPoint, look at the different types of friction, some of the scenarios and that sort of thing that gets covered. We're going to primarily look at the math part of it for this video. If you've gotten to the point where you've seen the equation, here's the equation to solve for frictional force. Pretty straightforward overall, but we'll have to kind of talk about some of the details. Um, Specifically, this is kind of the new character that pops up. This is the coefficient of friction. It's represented by the Greek letter mu, so that's what you're seeing here. We'll talk about that coming up. And then normal force is the other thing that we need, which is a little more familiar. We've been looking at that in the free body diagrams for a week or two now. So talking about this coefficient of friction, basically what this describes is a value that depends on the materials that are in contact. So some materials that are in contact are going to have a lot of friction. Some are not going to have a lot of friction. That's kind of what mu takes into account. What are we looking at? Because if you have something slippery like ice, you've got low coefficients. But if you have something like that's rough, like asphalt, you're going to have a high coefficient. So this specifically looks at what materials are in contact with each other. So that's kind of a little bit of a rundown on mu. Some values that you'll see, just to talk about those. If you have situations where you have like steel being pulled across steel, which is definitely like a high friction environment, you might expect a mu value of like 0.60. Versus if you have something slippery like ice being drug across ice, you would expect a lower value. So this is the way it's going to work. A high value here means higher amounts of friction. A low value here means lower amounts of friction. Um, these numbers can be looked up. There's lots of different resources to do that. Most of the time they'll be provided in the problem if you're not solving for them. But they are available and they get very specific. Like, um, and this one says like a piece of wood being drug across wood. It could be like as specific as saying a piece of oak being drug across a piece of pine, to get a very specific value there. So just to give you the heads up, the wood part might be something in the neighborhood of like 0.20, that sort of thing. So those are the numbers to expect if you solve for mu. So if you solve for the coefficient and you ever get something that's 1 or above 1, you've done something wrong. So these values should always be below 1, and then they'll depend on the materials themselves. Just looking at the number itself, you notice if we rearrange this equation, here's what we get. We get FF over FN for the coefficient of friction. And if you look at the units for this, like we usually do when we rearrange these things, we get newtons over newtons. And so the units will cancel, which means the coefficient of friction is just a ratio. There are no units attached, so don't expect that when you're reading through a problem. And then likewise, if you actually solve for coefficient, you're actually going to give just a number, which I know feels kind of weird at this point with all the stress that we've put on units, but no units for coefficient of friction. Okay, so let's just kind of look at how this is going to apply. If we look at something like diagram number 1 that we've been seeing in our free body diagrams, and we've been labeling stuff out. So we've had like applied force, and we've had FG, and we've been doing like normal force and all of that stuff. I'll go ahead and put those on. So we've had things like this. Basically, we've labeled frictional force, but we haven't done anything with it mathematically. So that's what changes now. So I'm just going to put some values in here. Let's just call this 20 newtons. Let's call FG 10 newtons. So let's say this is happening in this diagram. Excuse me. Once you see FG is 10 newtons, we of course know that Fn is also 10 newtons. That makes it kind of easy. And remember, that's important with the friction equation because we need normal force. This and the other diagrams, if you remember, normal force is a little bit more of a pain to solve out. And so even though this equation looks pretty straightforward, a lot of times it takes a lot of work to get this. And so sometimes this has to wait towards the end. Once you get normal force, then you can plug this in and get frictional force and go from there. So just want to kind of walk you through that. So let's say we've got a situation here. Maybe we'll use our the wood example. So let's say we've got a coefficient of friction here of 0.20. And so let's solve out frictional force here using our equation. So we can set this up to solve. And we can solve out frictional force here just by multiplying through. I think we get 2 newtons of force there. So we've got a frictional force here of 2 newtons. We can label it up here on our diagram if we want. So there we go. Now, if we were solving for the acceleration of this box or this object, whatever this is, we would have to find our net force. So we've got an applied force of 20 newtons, and we've got a frictional force now of 2 newtons. So we're going to have to figure this out. So we're going to solve this. We're just going to say F net equals 20 minus 2. So F net of 18 newtons of force. Just kind of ignoring sig figs just to run through this, but you got 18 newtons of force acting on this box. So now if you want to solve the acceleration, now you can do that. Now you would plug in and you would say F net equals ma. We would still need to find the mass of this, which we've been doing a whole lot of. So we'd still find the mass of this, which is going to be around 1 kilogram. Plug that in, and we can find the acceleration with friction being involved. So that's kind of the run through. Remember, like if you have diagram like number 2, where you have the object being pulled at the angle, remember here that normal force involves having to find this upward force and your FG. So a lot of times on like this diagram, it's going to take a lot more work to get normal force so that you can plug in to get frictional force, and then you can solve from there. This diagram, remember, I'm going to go ahead and put FF on here and FP. On this diagram, if you're solving for normal force, you'll have to do your subtraction. But if you're solving for the net force acting on this object, like if you're solving the acceleration of this thing, you're going to have to do FP minus FF. So FP minus FF on this diagram. And then if you're doing our incline problems, it's not a very good incline, but we'll work with it, where you've got this scenario going on. If this thing's sliding down the hill, so we call that like our FP, or our applied force by gravity. It's a really sloppy drawing. My apologies. We've got FF working up the hill. So in this diagram, what you would have to do, and then finish that off, to get your net forces, you're going to have to use FA minus FF. So F net here, FA minus FF. That's a question I get a lot of times, like how do I solve for acceleration? Like which of these 25 forces on this diagram are going to allow me to solve for acceleration? And in this case, remember, you got to get the net force. On this diagram, you're going to do FA minus FF. So it just kind of complicates the diagrams a little bit. We've been labeling it. We just haven't done anything mathematically with it. So hopefully that helps. As always, let me know if you have questions as you're working your way through.